Hi everyone, welcome back to my lecture. This video is the last part of Chapter 3. In this video, we will look at stack and subroutine implementation in microprocessor. We will first look at stack implementation and application in microprocessor. Stacks are conceptually last in first out, or in short LIFO, queues that can be used to describe systems from the architectural level down to the hardware level. When referring to hardware, generally these are areas in memory that have a variable length and a fixed starting address. Data is written, or pushed, onto the top of the stack, and also read, or popped, from the top of the stack, where the processor adjusts the stack pointer before or after each operation. ARM processors have a stack pointer, register R13, which holds the address of either the next empty entry or the last filled entry in the queue. This is how the stack is visualized. The stack is actually a part of the memory. This is bottom of the stack, and this is top of the stack. When we want to put data into the stack, we call push, where the first data will go to the bottom of the stack, and the last data will be at the top of the stack. Meanwhile, when we want to get the data from the stack, the operation is called pop. When we pop the data from the stack, the data at the top of the stack will be read first, and the last data to be popped will be the data at the bottom of the stack. This assembly program illustrates on how to implement the stack in ARM microprocessor. First, we define the stack address in the memory here, by using the EQU assembly directive. This means our stack address is now called STKAD. In this case, our stack address is hex 20,100,000. Next, we load the stack address into the SP register. Remember, the SP is the stack pointer. Then we load these 32-bit data into R0 and R1, respectively. Now, we will push the first data into the stack, where the data is from R0, followed by the data from R1. Then we pop the data from the stack to R2 and R3, respectively. For better understanding, you are required to run the code in KILE and observe the values in registers and stack. This is the illustration of what is happening in the CPU registers and memory when we execute the program in the previous example. When we have LDRSP equals STK_AD, and STK_AD is equate to hex 20,100,000, means the stack base address will be hex 20,100,000. When we load R0 and R1 with these values, then we will have these values in R0 and R1, respectively. Observe that the memory in this example is viewed in word format instead of in byte format as we have seen in the example before this. Therefore, the next address of the stack is hex 20,000,000 FC, which is hex 20,100-4. Then the next address is hex 20,000,000 F8 and so forth. After we push the content of R0 into the stack, the top of stack, or TOS will be hex 20,000,000 FC, where the content of the memory received the data from R0 like this. Note that, the data is arranged in little endian format. This means address hex 20,000,000 FC will has hex 78. FD will has 56, FE has 34, and the last one, address 20,000,000 FF will has 12. Next, when we push the content of R1 into the stack, the TOS is now updated to 20,000,000 F8, where the value from R1 is now in the memory address 20,000,000 F8 to 20,000,000 FB. Observe the value in SP, it will always point to the TOS. Now, when we pop the content of stack to R2, the content at the top of stack, in our case, is the content of memory addresses hex 20 million F8 to 20 million FB are now moved to R2 like this. The TOS or the content of SP register is now updated to hex 20 million FC. Then, when we pop to R2 again, we will have this value in R2, and the TOS is updated to hex 20,100,000. Now, let's see what is subroutine. Most large programs consist of many smaller blocks of code, or subroutines, where functions can be called at will, such as a print routine or a complicated arithmetic function like a logarithm. A large task can be described more easily this way. Subroutines also allow programmers to write and test small blocks of code first, building on the knowledge that they've been proven to work. Subroutine is called with the BL or branch and link instruction. This instruction transfers the branch target, the starting address of the subroutine, into the program counter and also transfers the return address into the link register, R14, so that the subroutine can return back to the calling program. Subroutines can also call other subroutines, but caution must be taken to ensure information is not lost in the process. We can imagine the subroutine using this flowchart. Let's this flowchart be our main program, and here we have another program, and this program is actually a subroutine. So, when we execute the instruction by instruction in the main program, and when we reach the line that we need to call a subroutine, here, the microprocessor will jump to the subroutine, execute all the instructions in the subroutine. When finished, we need to return back to the next instruction after the call, which is here. Then, execute the next instruction, instruction by instruction again, until we call the next subroutine, here. Then we jump to the subroutine again, execute all the instruction in the subroutine, then go back again. Let's look at this example for the application of stack and subroutine. And for better understanding, let's draw the flowchart for the program. So, here is our flowchart, where this will be the main program, and this one is the subroutine. Now, let's look at what the program do. First, we define the stack address. Then, we load these values into R0 and R1, respectively, meaning that R0 and R1 initially contain these values. Then, we call the subroutine, routine 1. Thus, we jump to routine 1. In routine 1, we need to save the contents of R0 and R1 in the stack, because we want to use R0 and R1 for other operations. If we don't do this, the values in R0 and R1 will be replaced with other values and there is no way to get it back. Now, for routine 1, we want to do this. Move hex 20 to R0, then, minus the content of R0 with 5, and save the result in R1. The operation for the subroutine is finished here, but before we go back to the main program, we need to load or retrieve the original content of R0 and R1. When we return to the main program, we then execute these instructions: logical shift left 10 times for R0, and logical shift right 10 times for R1. Finally, we add the contents of R0 and R1, and store the result in R2. Now, let's see how the microprocessor executes the subroutine. What happened to the PC and LR registers when the microprocessor executes subroutine? How the microprocessor keeps track with the program flow. In other words, how the microprocessor know where to go after executing the subroutine. Which is supposed to be the instruction after the BL instruction? The answer is the values in PC and LR registers. So, let's look at this illustration. These are the contents of the registers and stack just before the microprocessor executes the BL routine 1 instruction. R0 and R1 already have these values. This is the stack's base address, and this is the stack pointer, SP, points to this value. When the microprocessor executing the instruction just before the BL instruction, the PC will point to the address of the BL instruction, which is hex 400. Let's see these contents in Kyle Microvision. In Kyle Microvision, in the debug mode like this. Here is the disassembly windows, where we can see the address of our program in the memory, like this. And the machine codes of our instruction. For example, for the BL instruction, the address is hex 400. And this is the machine code, where the size is 32-bit. These are the content of registers, where we have the contents of R0, R1, already have these values. Also the content of SP and PC. Just ignore the content of the LR first, because we haven't called the subroutine. These are the memory windows, where we will see our stack content here. This is our base address, hence, here will be our stack content later when we pop the data into the stack. Okay, let's see what happen when we execute the BL routine 1. Now, when we execute routine 1, the PC will point to the routine 1 address, which is hex 410, which is the first instruction of routine 1, the pop instruction. Observe the content of LR, it is now updated to hex 405, which is the return address. Which means, when the microprocessor finish executing the subroutine, it needs to return to this address. In ARM microprocessor, the actual return address is actually the content of LR-1, which means, the actual return address is hex 404. Now, let's see the actual content in Kyle. This is the address of the subroutine, hex 410. And when we execute the BL routine 1 instruction, we will see the content of the PC and LR are updated to these value. PC contains the routine 1 address, 410, while LR contains the return address, 405. And the actual address is 404, the LR-1. When we execute the first instruction in the subroutine, the push, R0, R1. This instruction will push R1 into the stack, and follow by R0 into the stack. We now can see that, the TOS is now hex 20,000,000 F8, hence, SP is updated to hex 20,000,000 F8. The LR is still the same, but the PC is updated to hex 412, means the next instruction to be executed is located at address 412. Now the question is, why 412? The answer is because the size of the push R0-R1 instruction is 2 bytes, therefore it will occupy the addresses from hex 410 to 411, thus, the next will be 412. Let's see what happen when we execute the first instruction in the subroutine, which is the push R0-R1. Here, the values of R0 and R1 are pushed into the stack, here. And the value of SP is updated to hex 20,000,000 F8, while PC point to this address, hex 412. And when the microprocessor executing these two instructions, here is the content of R0 and R1, respectively. And observe the value of PC. Let's check in the Kyle Microvision, why we have hex 418 in PC. When we execute this MOV instruction, we will have hex 20 in R0. And the content of PC is updated to 416 because the size of this MOV instruction is 4 byte. As we have initially 412 in the PC, therefore, the PC will be updated to 412 plus 4, which is 416. Then, when we execute the sub instruction, here is the value of R1. And the value of PC is now updated to 418, because the size of this sub is 2 byte. The next instruction is pop R0 R1. This instruction will pop the content of the top of the stack into R0 first, before the next one is popped into R1. Therefore, when we execute the instruction, we will have these values from the stack in R0 and R1, respectively. Observe the TOS now is equal to the stack's base address, means there is no data in the stack, and the SP is now hex 20,100,000. When the microprocessor executes the instruction BXLR, means branch or return from the subroutine. The value in PC will be updated with the value of LR-1, which is the return address, or the address of the next instruction after the BL instruction. Let's see when we execute the instructions in Kyle. This is what happened when we pop R0 R1. We will have the values from the stack in R0 and R1. And this is the SP, where we have the stack's base address. When we exit or return from subroutine by executing the BXLR instruction, we will have this value in PC, hex 404, which is the address of the next instruction after the BL instruction. Next, we will look at a so-called nested subroutine, or in other words, calling a subroutine in a subroutine. In the previous example, there is only one subroutine, hence, only one return address is needed to be kept track. However, if we need to call another subroutine from a subroutine, there will be 2 return addresses that need to be saved. Therefore, BX instruction cannot be used in this case. In nested subroutine, the stack is used to store the value of LR as shown in the next example. In this example, we will have 2 subroutines. The first subroutine will be called from the main program, and the second one will be called from subroutine number 1. Now, we have these values in R0 and R1, respectively. And this is the stack address. Then we call subroutine 1 here. In subroutine 1, observe that, other than saving the value of R0 and R1 in the stack, we also need to save the value of LR in the stack as well. The reason for this is to save the return address for routine 1, because if we don't do this, when we call another subroutine from routine 1, the return address for the second subroutine will replace the return address of the routine 1. This definitely will crash your program. And when we call routine 2 here, we need to jump to routine 2, and save the values of the registers in the stack, if it is still needed for other operations later. In this case the value in R0 and R1. Observe that, here, no need to save the value of LR in the stack because we don't call any other subroutine from routine 2, hence, the return address for this routine 2 is safe in LR. And after the operations in routine 2, when we want to go out from this subroutine, we can use BXLR instruction as usual. Therefore, we will return to the next instruction after the call of routine 2, which is the pop instruction here. Now, the instruction is pop R0 R1 PC. Therefore, we will get back the value of the R0 and R1 before we execute the subroutine. Also, the value of return address of the routine 1 will be now in PC. This return address is the value in the LR when we push to the stack in routine 1. When we pop the value to PC, that value will be -1, just like we did in BXLR instruction, hence, we go back from routine 1 to here. You can observe the values of PC, LR, and stack for this example by executing this program in Kyle Microvision. Now let's observe this in Kyle Microvision. Before we execute the BL instruction, the PC has hex 400, which is the address of the BL instruction. Observe the next instruction after the BL is this MOV instruction, and the address is hex 404. This means the return address of routine 1 is 404. Therefore, we should expect the value in the LR must be 405 when we execute the BL instruction. Remember, the value in the LR is the return address plus 1. Now, let's see. OK, when we execute the BL instruction, the cursor indicates that we have jumped to the subroutine, and the value in the LR is hex 405. PC is now updated with the address of routine 1, which is hex 410. In routine 1, when we push the values of R0, R1, and LR to the stack, we can see that all the values are now in stack here. This is the values of LR. Now, let's execute all of these. And when we call the second subroutine, we should expect the value in the PC will be the address of the routine 2, which is 41E, while LR will has a return address of routine 2 plus 1, which is 41C plus 1, equal to 41D. Now, let's run. OK, now we have 41E, and 41D in PC and LR, respectively. OK, now let's execute routine 2. Until we reach BXLR. We should expect the PC will has the value of LR-1, which is hex 41C, and the cursor will go back to routine 1, the next instruction just after the BL routine 2, which is the pop. Let's see. OK, we have 41C in PC. Now, when we go out from routine 1 by executing this pop instruction, we should expect the value of PC will has the value from the stack, which is hex 405-1, equal to 404. Therefore, the program will go back to the address 404, which is the instruction MOV just after the call of routine 1. Let's see. OK, we have 404 in the PC, and we are now go back to the main program, at the MOV instruction. So, you can try to simulate the program in your Kyle Microvision for better understanding of the concept. Now, let's go to the last example for this chapter. This is a practical example, where we will look at the application for the microprocessor or microcontroller programming. Suppose that the ARM Cortex-M3 has the input and output registers at address hex 20,000,000 and hex 20,000,10 respectively. Bit numbers 0 and 1 of the input register are connected to switch 1 and switch 2, respectively. The output register is connected to 8 LEDs. Write a program to turn on the LEDs that are connected to the lower 4-bit of the output register, when switch 1 is pressed. Meanwhile, when switch 2 is pressed, turn on the higher 4 bits. If both are pressed, turn on all LEDs. Assume that 1 for input register, logic 1 indicates the switch is pressed, logic 0 otherwise. 2 for output register, logic 1 indicates the LED is on, logic 0 otherwise. This example can be illustrated like this. We have switch 1 and switch 2 connected to the ARM Cortex-M3 as the input to the microcontroller. Meanwhile, the output are connected to 8 LEDs. Here are the upper LEDs, which will be connected to the upper 4 bits of the output register of the microcontroller. Here is the lower 4 LEDs that will be connected to the lower 4 bits of the output register in the microcontroller. And the input-output or I/O registers are in the memory space of the microcontroller. In this example, let's assume that the input register is at address hex 20,000,000, and the output register is at address hex 20,000,1010. For the input register, bit number 0 will be connected to switch 1, while bit 1 will be connected to switch 2. And here is the output register, where the upper 4 bits are connected to these LEDs, and the lower 4 bits are connected to these LEDs. The operation is like this. When we press switch 1, the lower 4 LEDs will turn on, and when we press switch 2, the upper 4 bits will turn on. Meanwhile, when both switches are pressed, all the LEDs will be turned on. Here is the flowchart of this application. First, we need to set the pointer to the I/O registers. We can use any of the general-purpose registers. Then we turn off all LEDs. Then we test whether switch 1 is pressed or not. If press, we need to turn on the lower 4 LEDs, and go back test again. If still pressed, then we go to this path again. But, if it is not pressed, we need to check for switch 2. If it is pressed, then we turn on the upper 4 LEDs. Otherwise, we check whether both switches are pressed or not. If both are pressed, then we turn on all LEDs. Else, if no one are being pressed, then go back to turn all the LEDs off, and repeat the operation until you turn off the supply. OK, now let's look at the program. We set R0 to point to the input register, and R1 to point to the output register. Here, we turn off all LEDs by sending 0 to the output register. Observe that 0 is in R4, then we store this 0 using str instruction, to the address pointed by R1, which is the output register, in our case. Here we read the switches, by loading the content of memory address pointed by R0, which is the input register. We load using the LDR instruction, and it is loaded into R2. Then, we do the AND operation the content of R2 with number 3, and save the result in R3. Why we need to do that? This is to preserve the value of bit 0 and bit 1, which are the condition of the switches. And make sure that the others bit are clear to 0. Then, now we can compare with hex 1, if it is equal to 1, meaning that switch 1 is pressed and we need to branch to this label, because we use BEQ, branch if equal. In the switch 1 label, what we do is sending this value to output register. Hex 0F, means on the lower 4 LEDs, and off the upper 4. Then go back to the read label, here. Now, if we test here, if it is not equal to 1, we need to skip this instruction, and test for the next one. For the next test, we need to compare with hex 2. Why hex 2? Because hex 2 in binary is 1 0. Means we test, switch 2 is pressed or not. If pressed, we go to the switch 2 label, and do this. Sending hex F0 to the output, means turn on upper 4 LEDs. And go back to read again. And here, we test for both switches as pressed at the same time or not by comparing the input register with hex 3, or 1 1 in binary. If both are pressed, then it must be equal to 1 1 and we go to this both label. Turn on all the LEDs by sending hex FF to the output register. Then, go back to the label read again. But here, if not pressed, we just need to go back to this again, and repeat. Alright. We have finished Chapter 3 now. Please complete the tutorial questions given at the end of the lecture slide. We will continue with Chapter 4 in the next video. Goodbye for now, see you in the next lecture. Thank you.